Alright, today we are going to take a look at the last section in Chapter 2, Inverses. 473 and a half questions. Like the last question is just like, what is Yeah, if you get the exact equation I was thinking of and solve it, I get that.
That's pretty sick.
Alright, inverses. In order for a function to have an inverse, first of all, it must be what's called one-to-one. Does anybody remember what one-to-one means? And that's half of it. So that was our definition of a function, right? Every x has its own y. And every y has its own x. Okay, for it to be one-to-one, okay, we can say, like Riley said it, each x has its own y and each y has its own x, or we can say for each output, there's exactly one input, and for each input, there's did I say that? For each output, there's exactly one input, and for each input, there's exactly one output. Okay? There are no two y's that are the same, and no two x's that are the same, going back and forth. Right? So, I'll write for each output, there is exactly one input, and for each input, there is exactly one output. Okay? Another way of saying that is the graph passes both the vertical line test and the horizontal line test. Okay? So we can also say passes vertical and horizontal line tests. Right, that's the easiest way to think about the graph of a function being one-to-one. Right? If we draw a vertical line everywhere and it only hits one point, and we draw a horizontal line everywhere and that line only hits one point. Okay? So we talked about parent functions, what was that, section 2.6? Okay, that was the front of the note sheet. So which of our parent functions from that note sheet are one-to-one? So you can get out that note sheet if you have it, take a look at the front there, and see which of those parent functions are one-to-one, which have passed both the vertical and horizontal line tests. So which ones are one-to-one? Which ones pass both the horizontal and vertical line tests? Give me one.
X.
F of x equals x. What else? x to the 1/2 or x squared, yeah. Or, I'm sorry, it's square root of x, not x squared. What else? X to the 3rd. What else? Root of x. So we can say it's the 1/3 or cubed root. I think there's one more. Like 1 over x would also pass both the horizontal and vertical line tests. I think that's it for the parent functions. Right? Are we able to see what that means, right? Passing both the horizontal and vertical line tests. So that means that the inverse of each of these would be a function. Right? So if we think about these functions then, okay, thinking about what these graphs would look like, right? We shouldn't have to actually sketch out these graphs. Okay, this first one, 2x plus 5, that's a linear function. Is that going to be 1 to 1? Yeah, right? A line will be 1 to 1. It passes both the horizontal and vertical line tests. What about x squared minus 1? It's a parabola, right? So it's not going to pass the horizontal line test. How about 2 times the square root of x? What does that graph look like? Yes, right? That's just going to be a square root function. So, yeah, so visualizing things like this makes it even more important for us to know what the parent functions look like. Okay? Right? So, let's actually start talking about inverses, what an inverse is. So the notation for an inverse, okay, it looks like an exponent of -1, but it's not an exponent. Okay, we have to be careful not to confuse this with an exponent. Okay, we just write it as f to the -1 of x like that, but we read that as f inverse or the inverse of f. Okay, we don't say to the -1. Right? So a function and its inverse mirror each other. Okay, so what does that mean? Well, first of all, if we compose these functions, okay, if I take a function and its inverse, okay, and compose both ways, right? Take f inverse of f of x, or if I take f of f inverse of x, I should get x. Okay, when I compose and simplify, I should get x every single time. Okay, we'll take a look at that down here in this example, but first, let's take a look at some numerical examples. All right. So first, right, if I know that this coordinate point is on the graph, okay, the point 4, 7 is on my original graph of f. Well, what we know then, okay, the inverse, I should have moved that around. On the back, it tells us that we're going to have to switch these values, okay, but for every xy on the graph of f, the point yx is on the graph of the inverse. Okay, so what that means for this first example is if I know the point 4, 7 is on my original graph, the point 7, 4 is on the graph of the inverse. Okay, so f inverse of 7 would be 4. Right? If I know the point 4, 7 is on my original graph, the point 7, 4 is on the graph of the inverse. Okay, so in the second example, I'm saying that the point 5, -2 is on the inverse. So the point -2 what would be on the original function? 5. Okay. What's that? Alright. So given a function now, let's say we actually have a function of x to the 3rd power. We want to find each of these following values. So how would I find f of 2? plug 2 in, right? So this will be 2 to the third power, which gets me 8. Well, now I don't know what the actual inverse function is, right? We haven't talked about how to find the inverse yet. So how would I find f inverse of 8? What's that? Draw a check mark. So what we just determined is the point 2, 8 is on the original graph, right? The point 2, 8 is on the graph of x cubed. So we don't know what the actual inverse function is, but from what we just said, okay, if the point xy is on the original, the point yx is on the inverse.
So if we didn't do A, would we not be able to do B?
Right. So far, yes. We will get to a point where we could, but not yet. So if the point 2, 8 is on the original, the point 8, 2 is on the inverse. Alright? Well, now here, this is saying I'm going to compose these functions, right? F of f inverse of 15. Well, up here we said if I compose a function and its inverse, I should just get x. Okay, well, if we're plugging a value into that, I'm just going to get that value. Right? So composing a function and its inverse. So f of f inverse of 15 is just going to be 15. Okay? A function and its inverse are just exact opposite operations. Okay? They're inverse operations. Okay? Just like the inverse of addition is subtraction. Right? The inverse of multiplication is division. Right? Inverse functions just undo each other. So if I plug 15 into the composition of them, I'm going to get out 15. How about if I do it in reverse? If I take f inverse of f of 27.
Is it the same thing?
It's the same thing, right? Inverses just undo each other. Right? They give you a set of exact opposite operations. Right? So let's, down here, talk about testing to see if two things are inverses of each other. Right? So we're given two functions, right? The cubed root of x plus 1 and x minus 1 to the third power. To test to see if two things are inverses of each other, I want to evaluate f of g of x and g of f of x. When I simplify both of these, I should just get x. If I get x at the end of both of these, then these are inverses. So, to do this, first, let's take x minus 1 cubed and plug it in for x here. So, let's see, we'll have the cubed root of x minus 1 cubed plus 1. Right, so what's the cubed root of x minus 1 cubed? Yeah, right? Cube root and a cube cancel each other out. So this will just be x minus 1 plus 1. So x minus 1 plus 1 is just x. Okay? We can't stop there, though. We have to test g of f of x as well. So I'm going to take the cube root of x plus 1 and plug it in place of x over here. So we get the cube root of x plus 1 minus 1 cubed. Okay. Well, I've got a plus 1 minus 1 in here. Okay, I can go ahead and do that. So we just end up with the cube root of x cubed, which just gets me x. Okay, so if the composition both ways ends up to just be x, then these two functions are inverses of each other. Okay? These two functions give exact opposite operations. So yes, our answer is yes. These are inverses. Questions so far? All right, so let's talk about the graphs of inverse functions then. Okay, so we kind of mentioned this idea on the front already. If we have some point AB on f of x, then all I'm doing is switching the coordinates, right? Then the point BA is on the inverse. Okay, so if we have some point on the original function, I just switch the x and y coordinates, and that will be on the inverse. Okay, so what ends up happening then, if all I'm doing is switching the coordinates, a function and its inverse are symmetric about the line y equals x. Okay? A function and its inverse are symmetric about the line y equals x. So, if we look at this first example here, I'm going to sketch in the line y equals x. But what's going to end up happening? Okay, so we can either think about just kind of trying to reflect this across the line y equals x, or we can think about taking points, okay, and saying, well, so the point negative 2, 0 is on the original graph. That means the point 0, negative 2 will be on the inverse. So I'm going to come down here and plot point 0, negative 2. Right? The point negative 1, 1 is on the original. That means the point 1, negative 1 will be on the inverse. Right? The points, let's see, it's kind of hard to tell what that intercept is. All right, so let's go, we can see that the points then 2, 2 is on the original. Well, the point 2, 2 then will be on the inverse. Okay, so if we think about sketching this graph, okay, we should end up with something like this. And we can see that if we fold that across the line y equals x, okay, we end up getting a mirror image. Okay? So inverses are symmetric across the line y equals x. In other words, I'm literally just switching every single set of coordinates. Point negative 2, 0 is on the original, 0, negative 2 is on the inverse. Point negative 1, 1 is on the original, point 1, negative 1 is on the inverse. Okay so far? Alright, so why don't you guys real quick try this next one here. Okay, so it says we've got these 3 points on our original function. Okay, so graph some function. Okay, so you'll have may have different pictures here. Right? It just says graph some function that connects these points, and then sketch the inverse of what you just graphed. Okay, so plot those 3 points, connect them somehow, any way you want, and then sketch the inverse. So let me save this. That graph must.
So you just swap the x and y value to get the inverse. Do you change if they're positive or negative as well, or do you just move their spots?
You switch the coordinates. So if it was negative, it'll stay negative.
Oh, oh, there it is.
Did we get something like this? Okay, I just connected them with straight lines, but you may have connected them with curved lines, right? But this is the idea, right? The black is my original function, okay, with these 3 coordinate points. So all I did was switch the coordinates to get my 3 new coordinate points, and then I connected them with straight lines, right? So the original graph had -3, -5. My inverse has -5, -3. The original had -1, 2. My inverse has 2, -1. The original had 4, 3. My inverse has 3, 4. Okay. So all I'm doing is switching the x and the y coordinates. Okay? You okay? All right. So the last thing then is to actually find inverse functions. Okay. Given some function, how do we find its inverse? Well, so if we're given some f of x, okay, so let's say our first example is 2x plus 3. To find its inverse, first, we usually just think about place f of x, y. Right? So here, my first step would just be, well, I'm going to make this y equals 2x plus 3. Then, switch x and y. So here, I'm going to say this becomes x equals 2y plus 3. Right? Replacing all the x's with y's, all the y's with x's. Then, solve for y. So, to do that, see, I would subtract 3 over, and then divide by 2. So then the final step, just to get our notation correct, okay, would be replace y with our notation for the inverse, okay, with f inverse of x. So here, we would say x minus 3 over 2 less is equal to the inverse. Okay. So what we did, okay, we came up with a function that does the exact opposite as what we started with. Right? This function undoes this function. Okay? It does the exact opposite. Questions? Alright, so take 2 minutes and try B here. Replace f of x with y, switch x and y, solve for y, and then replace y with f inverse of x. So we get plus or minus the square root of x plus 1. Now, one thing I do want to mention for this, okay, earlier on the front, we said, well, in order for a function to have an inverse, it has to be one-to-one. Well, this graph is not one-to-one, right? It's a parabola. It doesn't pass the horizontal line test. But we just found an inverse function, right? What the front is saying is, in order for the inverse to be a function, the original graph has to be one-to-one. What we just found, okay, this plus or minus the square root of x plus 1, this is the inverse of this graph, but this is not a function, right, because it doesn't pass the vertical line test. So we found an inverse. It just isn't defined as a function. Well, this is the answer, right? This is the inverse of what we started with. It's just not a function. Right, this is the answer, the square root of, or plus or minus the square root of x plus 1. Right? But I just didn't want you to get confused and think, well, since this is a parabola, we don't have to do the problem. Right? There's no answer. There is. We can find the inverse. The inverse just isn't a function. Okay? So one more real quick here. Okay? On something like this, okay, the algebra tends to trip me up. So I want to go through this one real quick together. So the process is the same, right? Replace f of x with y, and then switch x and y, okay? So this would become x equals y plus 2 over y plus 1, and I'm just replacing all of the x's with a y. Now to solve something like this, well, I'm going to multiply both sides by y plus 1. I always want to get rid of the denominator whenever I can. So multiply both sides by y plus 1. So that would cancel these out. Now, I'm going to go ahead and distribute this x through. So I get xy plus x equals y plus 2. We talked about solving something like this a few sections ago. Okay, whenever I want to solve for y and I have multiple y's, I want to get all of the y's on one side of the equation and everything else on the other side. Okay, so I'll bring the y's over to the left and everything else over to the other side. So I'll subtract my y over here and then subtract this x over to the other side. Okay, so what I end up with is xy minus y equals negative x plus 2 or 2 minus x. Okay, so get all of the y's on one side, everything else on the other. Now the reason I do that is I can factor a y out of everything over here. Now I can divide both sides by x minus 1 and get y equals 2 minus x over x minus 1. Okay, so the key to solving something like this whenever I have multiple y's is getting all the y's on one side, everything else on the other, so that I can factor a y out. Okay, so then the last step is just to replace the y with the f inverse notation. So we've got 2 minus x over x minus 1. Okay.